The next proposition, we're going to show that measurable function behave pretty well with respect to taking limits and or lim sup, lim inf. Okay, so let's take a sequence of functions where you have some x to r. Okay, again, let's equip x with some some sigma alpha b. Okay, then I want to claim that the supremum of these fn, okay, is basically is a function where you just take the supremum of all the fn of x. Okay, so fn of x is a sequence of numbers in R, and the supremum is always well defined. Let's assume the supremum is not infinite everywhere. Okay, so let's assume this is not infinity. Okay, and similarly, you can define the infimum of these fn, and you can define, say, lim sup, and you can define the fn, and you can define the lim inf of these fn. Okay, they're all measurable. Okay, so measurable function behave pretty well with respect to these taking limits, basically. Okay. And finally, if you have a pointwise limit, suppose f of x equals to the limit of fn of x. Of course, this limit may not exist, so let's just assume for now it exists for all x. Okay, then we can show that f is also measurable. Okay, so basically the pointwise limit of measurable functions is again measurable. Okay. So again, this proof is fairly simple. Okay, let's just first of all consider the supremum of f. So let's let g of x equals to the sup of all the fn of x. And let's really consider what does it mean by g of x is greater than some number. Okay, so g of x being the supremum greater, if it's strictly greater than some a, well then you can know that one of these fn must give you a value that's strictly greater than a. Okay, so g of x greater than a will imply the fn of x greater than a for some n, so there exists an n. And the converse is also true. Okay, so if there is an n so that fn of x is greater than not 0 but a, well, then the supremum being greater than or equal to these fn, it has to be greater than a as well. So the backwards is also true. Okay, so you can write it as basically all the x where there exists an n where fn of x is greater than a. Okay, and you know this, if there exists an n, this is just simply saying the union. Okay, this is the union of all the fn of x greater than a. Okay. So when you take the union, it's basically saying the x has to exist in one of these fn greater than a, so that they are the same sets. Okay. Well, now you can see that this is in B, so their union is again in B, so this g of x is measurable. Okay, so the supremum is measurable. For the infimum is really just the same proof. Okay, so the infimum of fn is also measurable. That's basically as an exercise, essentially the same proof. And the lim sup and the lim inf, well, the lim sup is just really the infimum of the supremum. Okay, so here you can say this is basically the infimum. If I have fn here, then this is the infimum of k, and then I take n greater than or equals to k of these fn, so I consider the tail, and I take their infimum. That's basically how you define the lim sup. And we just show that the supremum of bunch of measurable function is measurable, so this is measurable. And now you take the infimum of a bunch of measurable functions. This is also measurable. Okay, so the lim sup is measurable, and lim inf is similar. Okay, lim inf of fn similar. Okay, because it's a supremum of the infimum. And finally, if the pointwise limit, these f of x equals to the pointwise limit exists, well, you know when the limit exists is basically equals to the lim inf or lim sup. Okay, that's when the lim sup and lim inf are gray. So you can say when it exists, it's simply the lim sup or lim inf. Okay, and you know this one is also measurable. Okay, because we just show lim inf and lim sup, they're measurable. Okay, so when the pointwise limit exists, you also have the pointwise limit is a measurable function. Okay, so basically this proposition just shows measurable function behave pretty well under taking limit. Okay. All right, and let's do two more things. So suppose I have some these x is equipped with some complete measure. Okay, so mu is a complete measure. Then I want to show that if f equals to g almost everywhere, okay, almost everywhere, basically it means the measure of all the x where f of x is different from g of x, okay, this set has measure 0, okay, so if two things are almost everywhere equal, then one is measurable will imply the other is also measurable, okay. So I want to show f is measurable implies g is also measurable. Well, let's try to prove this. Okay, so let's here I should give f, maybe f and g, they're both mapping from this x to some maybe y, where y is equipped with the sigma algebra C. Okay, so YC is a measurable space. Okay, so let's take any let's say f inside the range sigma algebra, so inside C. And we know that the f inverse of the set f is measurable, so it's inside B. Okay, so I want to show that f inverse, the G inverse of f is also inside B. Okay, so how do I show that? Well, let's consider what happens. So here you have the f inverse of f, and you will have a G inverse of f. Okay, so because f and g are almost everywhere the same, okay, so how do you get g inverse? Basically, you take away this red set and you add up the union up this green one, okay, that's how you move from the f inverse to the g inverse. And I want to show that these red and green one, they are actually always null set. So because mu is complete, you can remove things and add things up, and you will get a measurable set. Okay, so these two sets, this red and green one, their union is essentially the set difference you saw on your assignment. Okay, so let's use the same notation. This triangle f inverse g inverse f. Okay, this is essentially all the x where either f is inside the f inverse of f, but not g inverse of f, or the x is inside, well, not inside f inverse of f, but x is inside g inverse of f. Okay, this is how we define the set difference. And as you can see, if f is in the set difference, well, it means the f of x and g of x, one is inside f, the other is not inside f, so they must be different. So this is at least contained in the set where f and g differs. Okay, g of x and f of x, they're different. Okay, and the later one is a null set. Okay, this one has mu is equal to 0. So because mu is complete, we know that, so by mu complete, we know that these f inverse f, the set difference of g inverse f is also a null set. Okay, first of all, it's measurable and it's a null set. Okay, this is the definition of a complete measure. And because of that, well, this set difference is the red plus the green, and you can convince yourself the mu of the red one and the mu of the green one, they're all Lebesgue measure. I mean, not Lebesgue measure, but mu measure 0. Okay, so this G inverse of f, okay, how you get from the f inverse of f is essentially you take the f inverse of f, you take away the part that's only inside f inverse of f, so that's the f inverse of f, but not in g inverse of f. So this is the red one essentially, and you union up whatever is in g of f but not in f of f inverse of f. Okay, so let's say you union the g inverse of f, take away f inverse of f. Okay, so this is the green part, and either way they have the mu measure 0, so the whole thing is going to be measurable. So this is inside the sigma algebra B. Okay, so basically we showed if two things are almost everywhere equal, then one is measurable implies the other is measurable. Okay. And the quick corollary is the following. Suppose you have fn from x to, let's say, r measurable, and sometimes you don't have a pointwise limit, but you have a pointwise limit almost everywhere. So let's say this equals to x almost everywhere on some mu. So here mu is a complete measure on some sigma algebra B on x. Okay, so suppose you can have a almost everywhere convergence. Okay, then the function f of x is measurable as well. Okay, so this really follows from the fact that the limit is measurable, and if you have two things that are almost everywhere the same, then you have some measurable function. Okay, so this is really simple.